Our goal for this semester was to design a 3D printable prosthetic foot that met certain criteria. After drawing some sketches, we came up with this initial prototype.
We set the square infill to 50%. Our preliminary print orientation was the foot flat on the print bed.
We have designed our foot in a way so when it touches the floor during the stain phase, it would have shock absorption in the heel rocker. However, due to the material used to create the foot, a controlled design of the foot couldn't be achieved. Therefore, during the test, our foot was successful in achieving the shock absorption aspect as it bonded a bit after the shock.
The fracture that compromised the integrity of our product was a clean shear across the two fillets. This caused the prosthetic to completely separate into two solid pieces. Several refinements were made going forward. In our second print, the square infill was lowered to 30%. We changed the orientation to print on its side and added an extruded cut in the bottom of the prosthetic as a means of lowering the weight and minimally increasing energy return. This foot collapsed quickly under impact as a result of shearing in several locations. In our third and final print, we decided to change the infill pattern to hexagonal. The idea here being that this would make for more effective use of space, strength, and weight. It was our understanding from the previous two tests that we needed to revert back to the original print orientation for strong bonds to be produced in the correct locations, that being orthogonal to the build plate. As seen from the video, this design produced a more structurally sound prosthetic capable of dissipating the load without easily fracturing.
After testing the third prototype several times without it occurring any meaningful damage, we attempted a fully destructive smash test to observe how it would fail under catastrophic conditions.
With regards to what we can do going forward, it's important to note that we had a limited number of resources. In an optimal and ideal environment, we would test 10 or so differently designed prosthetics under consistent force. Dimensions to account for the ball, fillets, rounds, and the extruded cut at the bottom were all fairly arbitrary. A good idea would be to vary each of these dimensions at maximum and minimum values within a reasonable range, operating under the 2p factorial design of experiments, and see which would perform the best under a given load. The entire prosthetic was built using only one material, excluding the bouncy ball. In future iterations, it would be a good idea to consider a high-strength, flexible filament such as NinjaFlex.